Nintendo, hire me! Is the name of a difficult programming challenge from Nintendo European Research and Development, short NERD. It's basically a CTF challenge, and I would categorize it as a Kigenme. So the source code implements an algorithm that could be part of some software as a license key check. This code is probably the only Nintendo software you are legally allowed to crack, which I think is funny. The input you are allowed to control is here. So you have to find 32 bytes that when executing this results in the output to be the target string, hire me. On first sight, I thought this shouldn't be too difficult, but then I actually struggled a bit. In the first part, I tell you about how I approached this and what I tried that didn't work, and in the second video, we look more closely into my solution. Before we start, I briefly want to mention it's an ethical concern for me that if this is an actively used recruiting challenge, I don't want to ruin it. I believe the right thing to do is generally not to post spoilers online about something like this. But this challenge is over 5 years old and there exists already solutions online. So I don't think I'm causing actually any damage. Anyway, first step is obviously to get a rough overview of the code.
We have a big array called confusion with 512 bytes, a big diffusion array with 32 32-bit integers that look pretty random, and the input array. The main function is very short. It simply defines two arrays, the target and the output. The output is given to the forward function, and then afterwards 16 bytes of the output are compared with memCompare to the target. So the forward function should write the output, and we can see that the output is the second parameter of forward, which inside the function is called d, and it's written right here at the end. Easy. When you execute this little program, it doesn't print anything, nothing seems to happen, but it returns the result of memCompare, which, if you have some experience with programming and Linux, you know that it will be the exit code. And the bash shell can print the last exit code with $?. memCompare returns 0 when the compared bytes are the same, or non-zero when they differ. So when we execute this and look at the exit code, we see it's 10, which means the currently set input bytes do not result in the output to be equal to the string hire me. At this point I'm lazy and I don't really want to read the source code in detail yet. Maybe it's a simple algorithm and the solution can be simple too. So I decided to simply add a debug output that prints the generated output bytes. For that purpose, I write two simple for loops that go through the 32 bytes and print each byte, one time as hex value and one time as an ASCII character. Just in case you are wondering why I don't do simple printf instead of the single characters, it's because the output might contain non-printable ASCII characters, such as null byte, and the printf won't print the full byte sequence as ASCII. And for what I want to do next, I want to see each byte. You can also now see that the current input bytes lead to the output reverse me fast, which is obviously not hire me. So my first attempt to attack this algorithm is what in cryptography you would call a chosen plaintext attack. A chosen plaintext attack is an attack model for crypto analysis which presumes that the attacker can obtain the ciphertext for arbitrary plaintext. Maybe you wonder what this here has to do with cryptography. Well, this could be understood as an encryption. The input is 32 bytes and the output is 32 bytes. So you could also think of this as encrypting our 32 plaintext input bytes to the output ciphertext. Of course, the reverse could also be the case. Maybe this decrypts the bytes and what we have is a chosen ciphertext attack. It doesn't matter. The goal with both is to gain information that reduces the security of the encryption scheme. There are very fancy mathematical correlation attacks or whatever, and I have no clue about them, but a very simple thing you can test is, if I change one byte of the input, how does it change the output? If I change one byte and it only changes one byte on the output, it would be trivial with trial and error to find all the correct bytes. And so that's what I started with. I take the first byte here and change it minimally and look at the new output. But as you can see, the output changes dramatically. And this happens when I change the first byte, the second byte, or also the last byte. With the debug output, it's very clearly visible that changing the input minimally has huge effects on the output. So this very trivial attack is not possible. There might still be less obvious mathematical correlations you could statistically analyze, but I don't know how exactly. and I'm lazy. Damn it, I guess I need to dig deeper. This means I need to get a first overview of the algorithm. As you can see, the variables passed into forward are differently named than the ones used inside, so I want to clean that up. C is the input, D is the output, S is the confusion array, and P is the diffusion array. Now the code is a bit easier to read. The first thing I noticed was that the confusion array and diffusion array is never written to, it's never modified, it remains constant. And the confusion array is always only used as a lookup. They pass in a byte and take whatever byte is stored at this location in the array. I'm not a crypto expert, but I would call this an S box, and the original variable name was also S. In cryptography, an S box, substitution box, is a basic component of symmetric key algorithms which performs substitution. In block ciphers, they are typically used to obscure the relationship between the key and the ciphertext. And this is what happens here. Input is used here, but not directly. The input bytes are substituted through the confusion array. If, for example, the first input byte is a hex 2, then it takes the third byte of the array, so a hex 2 5. And that's the value we actually work with. The same happens down here. The internally calculated values are substituted before they are being placed into the output. In reverse, this means the output that we have as a goal, or our target hireme, are not directly the internal bytes of the algorithm. We need to reverse the substitution first. But reversing the substitution is kind of simple. We know that the byte hex 2 matches to the byte hex 2 5, which means if we have a hex 2 5, then we know the input byte must have been a hex 2. Easy. There's just one caveat, and that is that some bytes appear multiple times. In that case, it's not directly clear which one it is. It could be either, but I mean that just adds a small option, and when we try to reverse the algorithm, we can just simply try both options and see which one works. So after I realized that confusion is basically a S-box lookup table, I decided to remove it, just to mentally declutter the algorithm. Of course, we must not forget that it's there, but mentally I'm ignoring it for now. We know we can easily reverse the S-box, so I rather want to focus on the parts that might not be that clear. It helps to easier understand the algorithm. After that, I decided to go for another naive attempt because I'm hoping that everything will work out if I just start trying to reverse the algorithm. So let's get started. The function is called forward, so we can try to implement a backward function. This backward function has to do everything in reverse of the forward function. So let's think about the last part and how we can reverse it. We have the output given, and now we need to reason about what the internal input bytes were. When analyzing ciphers like this, you can think about what bias or knowledge does a number contain. One out byte is the XOR result of two input bytes, so the byte of the output carries some information from the previous bytes. More precisely, it carries the XOR result. If you know the XOR operation as well as its properties, you know that we have a problem, because we can't tell exactly what our 2 bytes were. However, we also know that if we guess one of the 2 bytes, then the other must be the output XOR that guess. Which means we don't need to brute force all 32 bytes of the internal input array, but it looks like we still would have to brute force 16 bytes. The other 16 bytes have the direct relation through XOR. Unfortunately, a byte has 256 options, which means a brute force would still be 256 to the power of 16, and that is still an unimaginably large number. We would never be able to brute force that. Once I had that realization, I accepted that I won't find a simple solution and I need to be more smart about my approach. Generally, the goal is now to find a way to reject or outright ignore bytes that would never be valid. So maybe there's a way to limit the brute force search space. But for that, we must understand the next part better. Let's look at that part by starting at the top. We see that most of it is wrapped in a loop executing this 256 times. So think about the very first iteration. In the very first loop, we take our input bytes that we control and that we have set to solve this challenge, and basically store them in the output array. And in the same step, we also reset our input array to 0. Of course, there is a substitution happening, we are not forgetting it, we just ignore it for now. Once this round is prepared, we can see that the outer loop counts j, which goes through each byte of the input array. And for each byte of the input array, it executes a loop over k, and k goes through the output array. On first sight, it looks maybe a bit crazy here, but it's pretty simple. First of all, in every loop, we are XORing the current value of the input array with out k. Out k is a byte set from our previous input up here, but it's multiplied with this expression. This expression actually has a bit mask of 1 and 1, which means the result of this expression is a single bit, which can be 0 or 1. So some out k's are multiplied with 0 and some with 1, which means not every out k is XORed into the input bits. A decision happens here which out k's are actually XORed onto the input. And the decision is made by the diffusion array. For each input byte, we select one of the diffusion array elements. For the first input byte, we select the first diffusion integer, then we loop through k, which keeps shifting the bits of this integer, and then masks the shift result to select the last bit. The first integer we use is hex F26CB481, and it has a 1 bit at the end. So we XOR out 0 into the input 0. But in the next loop, when k is 1, we shift now the diffusion integer by 1, and now there is a 0 at the end, which means out times 0 is 0, and XORing 0 onto the input has no effect. It's basically like we do not XOR that out byte. Alrighty, after this first round is complete, we go into the second round. Now the input here is not our input bytes anymore. The input bytes were totally scrambled by this XORing down here. But we store it in out again, reset input and XOR the new output bytes into the input. This is all done 256 times. Basically, this is a big XOR mixer. And when the mixing is done, we reach the last loop, which only loops for 16 bytes. It writes the actual output now. Each one of the 16 output bytes is the result of XORing a pair from the scrambled input array. This selects all the even bytes and this all the odd bytes. So the first byte of the output is the first byte of the input XORed with the second byte of the input. I want to make it clear that me talking through those individual steps doesn't mean I deeply understand it, and I don't expect you to understand it either. I'm literally just reading the code and transforming it into spoken English word. It's just a way for me to get familiar with the code and make you familiar with the code, and we just start thinking about it. There is a chance we notice something interesting, but it's not a guarantee, and I certainly had no idea yet. So let's approach it with the same thought from earlier. What information does a byte in the input array carry? Well, an input byte is the result of a loop with 32 XORs. But from earlier we know it's not really 32 times, it depends on the bits in the diffusion array. And the diffusion array is a constant, it never changes and it will always cause the same out bytes to be taken for the XOR. And I had the feeling that it must be something that we can attack it with. You know, XOR is self-inverse. XORing the same value cancels out. And imagine you have a long list of XOR operations. You can always pair up XORs of the same value and they cancel out. Take this as an example. This is a long XOR operation and it can be simplified down to just being the number hex for 1. And this line and loop is essentially a very long list of XOR operations.
But nothing in my brain clicked. I didn't see anything obvious that would allow me to cancel out most of the operations. So I'm still stuck. Damn. I slowly realized that this will take me longer than I thought it would. But now I already got started and I kind of promised somebody that I will look into it, and so now I must not give up. But I did take a break. I walked my dog and went to bed and tried the next day with a fresh brain. After this, I thought I need a bit more of a visual analysis, and I got out my notebook.
I started by drawing the out array again, which has 16 bytes. The next important internal values are from the input array. And now I can draw the bias mentioned before. This output byte is the result of the XOR from these two input bytes. And this obviously also applies to the other bytes. You knew this already, nothing new, just visualizing it. But now comes the block we have a harder time with. The loop takes values from the out array and puts XORed results into the internal input array. So here are the two arrays. And now the first input byte is the result of a selection of XORs of the values from the out array. And the second byte is the result of a selection of different XOR values from the out array.
I was hoping by drawing this, instead of trying to imagine this, I would have an easier time to find a pattern. I mean, if the brain is not busy retaining this information and I can concentrate on potential relationships between the different parts, there's a higher chance to notice something.
And so I'm ignoring the first stage now, and I just try to think, if I had the input array bytes, how could I get to the out bytes? The first and second byte of internal input might include some of the same XOR values from the out array. This means both result bytes carry some information about the same bytes, which means there's also an indirect relationship between those two. For example, if we would try to brute force possible out array values so that the first input byte is correct, then this has a direct effect on the second input byte. And if we now try to find valid bytes for the second byte, we cannot touch the XOR values we used in the first byte. Otherwise the result is wrong again. And I start to get the feeling this feels like a logic puzzle. Now remember the brute forcing problem of the first stage. I was wondering if the relationship and the dependencies between those input bytes can be used to quickly reject invalid candidates or even use it to somehow generate valid inputs.
Again, saying those things doesn't mean I know how to do that. It's just what I'm thinking and what I'm looking for. I still haven't had an epiphany. And I think it's time to take a break again. I did not solve this challenge quickly. It took me multiple days with breaks in between to keep thinking about what else I could try. So, now that you have gotten a first overview, feel free to try to solve the challenge yourself. I think you learn a ton by just trying it, and you have the whole week. And next week I tell you how I solved it, and you can then compare your notes or solutions to mine.